Good afternoon. It's great to be here. Year 1958, Jack Kilby from Texas Instrument first invented what is called as a first integrated circuit. And that was the beginning of a semiconductor era that changed our life forever. In fact, it impacted our life in every moment. In fact, right now, at this very moment, I'm talking with you, it is basically because of this media that I'm talking with you. It's controlled by the chips. In year 2022, just last week when I was preparing for coming down here, IBM introduced, there are 2 nanometer chip technology. And there you have about 333 million transistors per mm square, and about 50 billion of those per chip. So in these last 64 years, there is tremendous progress that happened in a single material silicon in every aspect. It's going from materials development to the architectural level, even at the device level, innovation in lithography, as well as in a semiconductor fabrication technology, that really helped to get to where we are in these 64 years. But we are coming down to very fundamental limits, which is the atomic distance between the silicon is just like 0.5 nanometers. So we really have to think about where this technology is going to go. And when we talk about having these chips, into the exascale supercomputer like this, there is a lot of resources that needs to run this supercomputer. It takes about 50 megawatts of power, and if you look at the associated budget, about 20 to 30% of the cost is just needed for water cooling. So that's a tremendous amount of resources that are putting, including EUV lithography, to really make this silicon engine works. So this is really time to think about other materials technology. There are already other materials, including diamond, and I think diamond is a fascinating material, as we know from centuries, because of its brilliance, value, and of course it's called girl's best friend. But now it's called scientist's best friend because of its extraordinary materials properties. For example, high dielectric strength, which basically is very important for the power electronics because it isolates about 10,000 volts with just 20 micron chip. The other important property is radiation hardness, because diamond has a very robust structure. So even high energy particles like proton, alpha, and gamma rays, don't disrupt the diamond structure. If you use silicon, it will just get, fried at this high energy. And the third and very important property is very high thermal conductivity. So diamond is the highest thermal conductivity of any other material, and it is isotropic, which means in every direction. Diamond has a 5 times higher thermal conductivity, 22 times higher than the silicon. So all these properties make diamond is an interesting material and very promising material for semiconductor technology. Now, any new technology that you introduce in this time and age, it's really important its implication from the environmental perspective. We should not disturb the environment, as well as we not add anything, to cause disruption in the environmental climate. So we can grow this diamond, using a lab, microplasma CVD process. And the gases that we use here is greenhouse gases like methane and CO2. And in fact, there are technologies that you can capture CO2 directly from air and create diamonds. So it turns out that it takes about 20 tons of CO2 to make 1 carat of diamond. Whereas if you go to the mine diamond, it takes about 250 tons of earth removed, and not to mention about the ecosystem that goes with it per diamond. As well as it saves about 127 gallons of water if you use this CVD diamond technology as opposed to the mines. So definitely there are various ways that that shows us that diamond is the material of choice for the semiconductor electronics. Now you'll ask me, why on earth this material is not in the my chip yet? Now there is questions. This is a good question, and in the last 2 decades, there's a lot of progress that happened on the CVD diamond. A company like E6, Element 6, mastered the process to create a very high quality diamond as shown here. But there are still fundamental challenges. For example, seed size. Diamond is available only from millimeters to few inches. Controlling defect density, that's very important for any semiconductor material. And lastly, the N-type doping. In this case, phosphorus is used generally, which is larger atom size. And when you try to dope it, it creates a lot of strain into the diamond and creates defects. So these are the fundamental problems why diamond did not become a semiconductor material of choice. Until now, this change is happening with what's called as Stacktronics. And thanks to the material like graphene, because of graphene, we know that with this 2D material, we can stack just like a Lego brick. And because of the proximity effect, we can get interesting changes in the device properties. In a similar way, what we are doing is we're taking diamond and then stacking other 2D materials on top of it. So in this case, what we have shown is that if you take a diamond and then stack graphene, you can extract very high current density, the current density equal to the superconducting wires, but at room temperature. In another case, we can take N-type MOS2 and then stick onto the P-type diamond, and it shows excellent PN junction properties. So these are excellent properties, and this way, the possibilities are endless to create 2D structures of different material on top of diamond. Now, where we are going with this? You can think about diamond by using smart cut technology, so you can make the copies of the diamond, so there is no question of large area. And since it's 100 nanometer, you can think about reducing the defect density. Also, you can create a library of these 2D materials, and using AI ML guided approach, you can already predict the properties of what other material could we stick to the diamond, and what kind of properties you really want. So we are already going in this direction, and we think that this will become a way to become a mainstream semiconductor material. We already see a future in various areas, for example, in power electronics, in space application, in avionics, as well as in automotive electronics. We already know the power of diversity, at workplaces, in everyday our life. In fact, this is the main, a key piece of our human evolution. And the Mother Earth already has shown the same thing works in materials. So let's embrace the power of diversity in materials for the future of microelectronics. Thank you.